Hello, and welcome to your Chemistry 1412 mini lecture that gives an introduction to equilibrium and also covers Le Chatelier's principle. We will be doing equilibrium for this lecture and the next 6 lectures, so setting a good foundation of understanding is important. Equilibrium does not mean that reactants and products are equal in amount. Instead, it means that for each reactant that turns into products, there are products that turn back into reactants. Equilibrium implies a fast, reversible reaction. Equilibrium could be established in a reaction in which the final reactant amount is quite high, while the product amount is quite low. Equilibrium may also occur when the amount of products is high and the amount of reactants is very low. Very, very rarely does equilibrium occur when the reaction has progressed to the halfway mark. The double-headed arrow in a chemical reaction is an indicator that this reaction achieves an equilibrium. The equilibrium constant K is a measure of the magnitude of how far forward a reaction will go before it reaches equilibrium. When you have a reaction that is in the gaseous phase, the equilibrium constant K is the ratio of the pressure of the products to the pressure of the reactants. When you have an equilibrium in the aqueous phase, it is the ratio of the concentration of the products to the concentration of the reactants. If the value for K is more than 1, then you know that the equilibrium is product favored. The larger the K, the more product favored it is. If the value for K is less than 1, then you know the equilibrium is reactant favored. The smaller the K, the more the reactant favored it is. Product favored means that at the moment of equilibrium, there are more products present than reactants. Reactant favored means that there are more reactants than products at the time of equilibrium. To get to the number to which K is equal, one takes the pressure or concentration of the products raised to their coefficients in the balanced equation and divides by the pressure or concentration of reactants raised to their coefficients. This general form of the equation is used for all equilibrium expressions. In order to relate the K of pressures to the K of concentrations, one must take into account the difference of the moles of gas between the products and the reactants. This is the equation which does so. Notice that if the moles of gas in the pressure reaction are the same for reactants and products, then Kc is equal to Kp. When there is a liquid or a solid in a reaction, those values do not appear in the equilibrium expression. The reason is as follows. Equilibrium expressions include pressures and concentrations. There is no such thing as a concentration of a pure liquid. Concentration implies a solution with a solvent and a solute. Also, there is no pressure of a solid. Only gases have quantifiable pressures. This means you completely omit liquids and solids from the equilibrium expression. When you are not sure that a reaction has reached equilibrium, but you are able to measure either the pressure or the concentrations involved. The equilibrium expression becomes the reaction quotient. It is calculated via the same method as the equilibrium expression, but instead of setting it equal to K, you set it equal to Q. If you find that Q equals K, then you have verified that the reaction is at equilibrium. If Q is less than K, the reaction needs to go forward to reach equilibrium. If Q is greater than K, the reaction has overshot the equilibrium point and needs to go backwards to get back to equilibrium. You might wonder how a reaction is able to overshoot equilibrium. Here is how. If you dump a bunch of products into the reaction vessel, it will have more products present than would have been there at equilibrium. This disturbance of equilibrium causes a shift to occur, to go back to achieve equilibrium. If a reaction suddenly has too much product present, then the reaction will shift backwards to use up that extra product by making it back into reactants. That same shift occurs if you remove reactants, as this makes the reaction vessel contain too many products in comparison. If you have a gaseous reaction, changing the pressure of the reaction vessel will cause the equilibrium to shift. If you increase the vessel pressure, the equilibrium will shift toward the side with fewer moles of gas, thus lowering the spike in pressure. If you decrease the pressure of the vessel, the equilibrium will shift towards the side with more moles of gas to alleviate the drop in pressure. One can heat or cool a reaction in order to shift the equilibrium as well. If a reaction is exothermic, then you can consider heat to be a product. Adding heat is adding a product. Therefore, the reaction will shift backwards to use up that extra product. If you cool an exothermic reaction, you are removing a product. Hence, the reaction will go forward to replace the missing heat product. The opposite is true for endothermic reactions, in which you would consider heat a reactant. One can relate the equilibrium constants of a reaction at two different temperatures with the equation shown here. Take care during calculations to write all units and make sure they are canceling. The heat of enthalpy is normally given in kilojoules, while the constant R is in joules. Also, be sure to use Kelvin temperatures in the calculation. This has been your mini lecture over equilibrium and Le Chatelier's principle. Please go to Sapling now and complete your post-lecture assignment. If you run into trouble or get stuck, do not hesitate to ask for help. Help is always available.